So what I'd like to discuss today are a handful of topics that relate to what happens later. Okay, so how we go from small particles of solid material, rocks and ice in the disk, up to planetary systems. Okay, so I'm not going to make any pretense of giving like a complete discussion of later stage physics. Instead, what I want to do is actually discuss 2 or 3 topics that are fairly topical, where there's a lot of work recently. One of them is something that my group has been working heavily on. A couple of others are ideas that are quite popular today in the literature. So I just want to give really a flavor of some important pieces of physics that occur at later times. Okay. But first of all, let's just say one more thing about the small particles. At the end of yesterday, we were discussing radial drift, and the main point was if we have objects that are embedded within the gas disk, they have a tendency to spiral in towards the star under aerodynamic forces. And that's true whether they're small dust particles or whether they're larger objects. And the timescale for that spiraling can be rather short, and that creates a problem in understanding how we go from objects perhaps of centimeter or meter size up to things that are kilometer size and larger. Now, one way around that problem, at least in part, which was actually discussed yesterday also in Leonardo's talk, would be if the gas disk does not have a smoothly declining pressure profile in the midplane with distance from the star. Because you'll remember that the reason that the material was spiraling in was because the pressure decreases outwards. There's therefore a pressure gradient which tends to support gas against gravity, and so the gas rotates in a slightly sub-Keplerian sense. Now, if we can engineer a situation where we have a local pressure maximum, then in the rising piece of the pressure profile, all of that argument is simply reversed. Okay? So in that situation, particles will drift in wherever this slope is negative, but they would tend to drift out where it's positive. So if nothing else goes on, you can imagine that there'll be a trap here, and as the material flows in, it will simply accumulate in a ring or an annulus at this radius. Okay. So that could be an important piece of physics, and it's gained a lot of popularity recently, given the fact that we do observe these rings, at least in dust emission, in a number of disks that are observed at high resolution with ALMA. Okay, so there's some, let's say, observational evidence that suggests that the formation of ring-like structures is not implausible. Okay. Now, of course, if those ring structures are actually formed by planets, that doesn't really help the situation very much. But as we'll discuss tomorrow, and was also discussed yesterday, there are processes that can form rings even in the absence of planets. Okay, and so this is just a preview of things to be discussed tomorrow. There are sort of 2 or 3 different ways in which you could form pressure maxima of different kinds that might play a role in trapping solids. Okay, so one class of structures would be, if you like, transient or perhaps not entirely long-lived structures. So that would include the zonal flows, which would really be rings of high pressure around the star. You could also do a similar thing with non-axisymmetric structures in the form of vortices. Okay? And the idea that vortices play a role in planet formation is an extremely old one, sort of dating back before the modern understanding of planet formation, but it's something that continues to attract quite a lot of attention. So one idea is these kind of transient structures that develop out of turbulence. So you might sort of imagine these, loosely speaking, as being a sort of large-scale cascade, which is producing large-scale structures in a turbulent flow. Another possibility is that there may be fixed locations in the disk, or roughly fixed locations in the disk, where the structure of the disk changes in such a way as to produce a pressure maximum. And so those changes might be associated with differences in the efficiency of angular momentum transport as we go from different non-ideal MHD regimes. They might also be associated with chemical transitions due to having the snow line or to perhaps having other chemical transitions within the disk. Okay. So again, we'll say more about some of those things tomorrow. Okay, but let's now go on to how we might produce planetesimals despite the fact that we have this rapid radial drift, which is producing a barrier to planetesimal formation. So the idea here is one of collective instabilities. And most of these, I think I would probably say all of these, share a sort of common feature, which is based on sort of a thought experiment. Suppose we could actually settle the solids in the disk down to a reasonably thin layer near the disk midplane. Okay? So suppose we get to a situation where the solids have a density that exceeds the Roche density. Okay? So the Roche density is the stellar mass divided by r cubed up to some numerical factor. Okay? So this is commonly encountered in discussions of planetary satellites, because if you have a planet and then you have satellites around it, the Roche radius, which corresponds to a Roche density, is the radius inside which the tidal gravity from the planet would act to unbind a satellite. So the gravitational force, the tidal gravitational force across a body would become larger than the self-gravity force that is trying to hold it together. Okay? So if you can get to a situation where the solid density exceeds this number, then actually self-gravity in the solids themselves will cause that material to collapse radially. Okay? So if you can do that, then what you could do is you could take a relatively thin layer of dust or particles that's thin and dense. It would collapse under gravity, and then it would basically break up, and during that collapse process to form bound objects. Okay? And in old classical pictures of planetesimal formation, the characteristic size of those objects would be a few kilometers in size. Okay? So the picture would be, maybe you have dust, settles vertically, becomes very dense, and then those clumps of dust just collapse gravitationally to give you the planetesimals. Okay? Okay, so what's the attraction of this? Well, the attraction of this is that basically this means that the problems we were discussing yesterday that are associated with radial drift and with the material properties of like sticking of rocky materials become irrelevant. We can sort of bypass them fairly easily. So if you imagine a sort of timeline of sizes of particles going from very small things, micron sizes, up to kilometer sizes, we've already said that from maybe micron sizes up to millimeter sizes, direct coagulation of those particles seems to work quite well. So as far as we see, both based on experiments and on sort of simpler considerations, there's nothing to stop those particles hitting each other frequently, sticking together and growing into larger objects. So we can reach at least millimeter sizes for rocky materials, maybe centimeter sizes also for rocky materials, maybe sizes rather larger than that if we're dealing with water ice materials that would be further out beyond the snow line in the protoplanetary disk. And then if we have this gravitational instability, we can take clumps, very large clumps of these relatively small particles and collapse them gravitationally up to maybe 10 kilometer sizes. And the attraction here is that, well, first of all, we completely bypass the intermediate size regime. So the fact that meter-sized rocks don't stick together very well on collisions becomes irrelevant to the story. And moreover, the timescale for this is basically the dynamical timescale, the free-fall timescale, and that's going to be very short. That's going to be of order the orbital timescale, or maybe tens or hundreds of times the orbital timescale. So the fact that at 1 meter or thereabouts you might drift into the star on 1,000-year timescales, again, that doesn't matter because you never had meter-sized objects existing in the protoplanetary disk in any significant number. Okay. So this is an attractive picture, and in fact it is the original model for planetesimal formation. Okay, so when Safronov was working on this in the 60s, and actually he references even earlier work going back to the 50s, and Goldreich and Ward also at the end of the 60s and the early 70s, this was how they imagined that you got to planetesimals. Okay, so they didn't particularly consider radial drift, and they didn't know very much about these material barriers to coagulation growth, but they thought that this gravitational collapse was rather a natural way to make kilometer-sized objects. Now, the problem with this is that this Roche density is very high. Okay, so it's about, for sort of standard parameters, it might be 100 times the gas density in the midplane. And if initially you start with 1% of the material in the disk in the form of solids, the rest in gas, you need to basically invert that gas-to-dust ratio. You need to go from locally gas being a factor of 100 dominant over solids to solids being 100 times dominant over gas. And as we discussed also yesterday, it's actually quite hard to obtain such high densities. And in particular, turbulence prevents settling. We noted that it had that sort of square root dependence. So even if you wind the turbulence down, you don't really make the dust layer that you can form that much thinner. And even if there was no turbulence, there will be this Kelvin-Helmholtz turbulence generated by shear, which would preclude you from reaching these very high densities. Okay? So this argument was made most clearly by Cousy and collaborators now way back in 1993, 25 years ago. And this was pretty quickly accepted as being a very serious objection to this gravitational collapse story. And actually people went back to thinking, how can you get around these material barriers in the meter size regime? But we can do things in a little bit cleverer way. Okay. So the cleverer way is to appeal to additional instabilities beyond gravitational instability. And the basic idea is that if you can get to a regime where the solid density is sort of at least roughly comparable to the gas density, then at that point, if you like, the solids and the gas compete on an equal footing for the dynamics of the disk. So in that regime, it's not the case that basically you just have a gas disk and the solid material is sort of passively evolving within the gas. The aerodynamic feedback that the particles are putting back into the gas themselves becomes dynamically important for the gas. So both the gas and the solids have interesting dynamics, and that coupled dynamics can give rise to new instabilities. Okay. So the instability that we're going to be discussing is described as the streaming instability. This is the original paper from Andrew Udin and Jeremy Goodman, and it's a local instability, a linear instability of aerodynamically coupled mixtures of gas and solids. Okay. Now, to get to this condition where the solids and the gas sort of compete on an equal footing, you still require a strong concentration of solids. Okay? Because remember, the solids initially are only 1% of the gas. So you're not guaranteed to be able to reach those conditions, but it's still much easier, basically another factor of 100 easier, than direct gravitational instability. Okay? So the story here would be a one with an additional step, basically. The first step remains coagulation growth of dust particles up to maybe millimeter or centimeter sizes. Those will then settle vertically in the disk, as we discussed yesterday. In the region where the particles have settled, their local density starts to become comparable to the gas. You then trigger this streaming instability, and then the idea is the streaming instability would get you that next factor of 100 to get you to gravitational collapse. Okay, so does that work? Okay. Well, the first question is, what does this linear instability look like, and what physics is really going into to describing that? Okay. So this is the equation system that was looked at in Udin and Goodman, which forms the basis for this kind of analysis. So what we have here is we have two fluids. We have a particle fluid, and we have a gas fluid. Okay? And we do not consider magnetic fields here. We do not consider, in this analysis, self-gravity. And we do not consider any thermal effects that might require us to look at an energy equation. Okay? So we assume that the gas is just isothermal. So in that situation, you just have continuity equations and momentum equations, but there are two of them, one for each of the species. Okay? So we have a continuity equation for the solids, which are here being treated as a fluid, and we assume that the gas is incompressible, so we don't have to worry explicitly about a continuity equation for the gas. Okay? So the assumption here basically is that the motions that are being introduced by this streaming instability are going to be small, and so the density fluctuations that are associated with it are small and negligible. And then for the particles, we have, for the particles and for the gas, we have momentum equations. So here we have a momentum equation for the gas, involves a pressure gradient. Here we have one for the particles, which does not involve a pressure gradient. And both of these have terms that represent aerodynamic coupling between the particle fluid and the gas fluid. So the thing that matters is the relative velocity between the particles and the gas at each point, and then the aerodynamic properties are all encoded in this stopping time, which is this quantity I defined yesterday, which was m delta v divided by the drag force. Okay? So the Uden and Goodman analysis is a linear analysis on this set of equations, where the background state is the equilibrium state, where the fluid and the gas, the particles and the gas are just evenly mixed. Okay? So in that circumstance, the particles are all drifting inwards, and the gas is drifting outwards to conserve the overall angular momentum of the system. Okay? So that's where the instability, or that's the system that is solved to look for the instability. You might ask, physically, why should this coupled system develop an instability? And this is actually quite tricky, because the linear phase of the streaming instability doesn't really have a very simple physical interpretation. So you may have heard when we've been discussing the magnetorotational instability earlier in the week. There's a very popular way of thinking about that in terms of springs, which connect fluid parcels in different regions of the disk. Okay? So in that system, you can develop a sort of simple mechanical analogy to understand why the mathematical system ought to be unstable. For the streaming instability, that's not really the case. Okay? There are some discussions of where the instability comes from, but there's nothing that you can state in just a few sentences to really understand why this system should have an instability. Okay, so that's the linear phase. I should mention that the nonlinear phase, which is actually what we'll be showing simulations of a little bit later, does have a simple explanation, or an analogous explanation at least. And the one that is perhaps most visual is that of a peloton in a cycling race. Okay, so you know that if you're cycling, at least if you're cycling at sort of professional cyclist speeds, then aerodynamic drag is an important thing. Okay, and so that will limit your speed. And so a bunch of cyclists in close formation can benefit because they collectively break the headwind, and so most of them only feel a fraction of the total headwind which is associated from the group. So the idea in the streaming instability situation would be that if we have a dense clump of particles, think of this as the dense clump of particles, locally that would accelerate the gas that is around it, and then because it's accelerated the gas, the headwind that those particles feel is less than the average headwind elsewhere within the disk. Okay? So that reduces the local speed of radial drift, and then the clump will grow as new particles spiral in from further out. Okay? So that would be the story. By sort of gathering together in a dense bunch, the particles can partly prevent the radial drift. Once the radial drift is slowed, other particles further out that are experiencing the full radial drift move inwards and join them. The clump becomes larger, and therefore it slows even more. Okay? So that's quite a good analogy, and it probably is a description of what's going on in the nonlinear phase of this instability. But unfortunately, this is not actually a linear phenomenon. Okay? So it doesn't explain why the system is unstable in the first place. It only explains what would happen once you really get some clumping going. Okay, so that's the analogous version. Here's just some plots from Uden and Goodman. Here's that system of equations again, and the parameters that matter here, there are basically three of them, and two of them are shown on this plot. Okay, so one of them is the stopping time. So this is this dimensionless stopping time that I introduced yesterday. So here we have a very weak, very strongly coupled aerodynamic particles, very small particles, and we're going up to larger particles as we go up in this vertical axis. And here we have the particle density divided by the gas density, going from the mean value in the protoplanetary disk, 10 to the minus 2, up to situations where the particle density is locally quite high compared to the gas density. Now, the Uden and Goodman analysis is in an unstratified vertical medium. Okay? So there's no vertical settling, because if you don't have turbulence, there's no equilibrium state that would result from vertical settling. Right? If you have vertical settling, then if you don't have turbulence, the particles would just settle into an infinitely thin sheet. Okay? So in a vertically stratified disk, unless you include something about turbulence, there is not an equilibrium state which you can then perturb and do a linear stability analysis of. So the Uden and Goodman analysis ignores the vertical component of gravity entirely, so there's nothing to cause the particles to settle. And so this gas-to-dust ratio would just be the total gas-to-dust ratio in the disk at that radius. Okay? Now, in reality, obviously, you'd have to interpret this as being something like the dust-to-gas ratio in a settled particle layer, where the layer thickness is determined by turbulence. But that would be not an exact mathematical correspondence there. So those are the two parameters that are plotted here. There's a third parameter, which is the streaming velocity. What is the difference in the azimuthal velocity between the particles and the azimuthal velocity of the gas? Okay? So that will depend on the pressure gradient and the density gradient in the gas disk, and it will be a small number compared to the Keplerian speed. But it's that streaming which is ultimately providing the energy source for the instability, and so it will also affect how the instability develops. Okay, so that's what this plot shows, and the lines and the contours here are showing you the growth rate of the instability. Okay? Now the growth rate can be quite high, so this is -1 here, so this is basically a tenth of the angular frequency if the particles are quite large. Okay? But then as you go to very small particles, this linear growth rate drops by several orders of magnitude. Okay? So over all of this plane, actually, except at a singular location, which is where these densities are actually 1, the instability exists, but only in some regions of the parameter space is it actually quite vigorous. Okay? So it's not as fast as the MRI. It doesn't grow on omega to the -1. At best, it maybe grows at a tenth of that. Okay? But nonetheless, this gas-dust system is unstable, and that ought to give rise to clumping of the dust. And the question then is, how strong does that clumping become? Okay, so let me just show you a movie done for a planetarium show of this kind of instability. So this is actually a non-ideal MHD simulation of a protoplanetary disk done by Zhao Zhu at UNLV now. And in a minute, we're going to transition to a second simulation done by Jake Simon, which looks at a very small patch of the disk and shows this streaming instability in action. So here we've zoomed in, and now we're looking at the particle density in the system, and you can see the development of this stream, annulus, of particles, and then within it, gravitational instability is causing clumps of those particles to collapse and form planetesimals. Okay? So in the big picture, that's how we think this mechanism might work to produce planetesimals. It's sort of a two-stage thing. You get particles settling, you initiate this streaming instability, and then you get dense clumps which collapse gravitationally. And this was a planetarium show, so all of the remaining steps from going from a few kilometer-sized planetesimals to giant planets that open gaps in the disk were swept over, and we zoom out and we see that. Okay. Show that one more time. Yeah, so this is actually showing structure developing from non-ideal MHD in the gas and particles. And so this is a global calculation, of course. This streaming calculation we zoom in on is really on a very small scale. So the simulation domain is only 2/10 of a gas scale height in each direction. And that's because these particle gas instabilities operate on substantially smaller scales than the overall, even the thickness of the disk, much less the radius. Okay. So there, we have this collapse. Okay, so now I'm going to just show some more quantitative results from these kind of calculations. As I was saying, these instabilities occur on quite small scales. Okay? And so it's hard to do them even in simulation boxes that are large enough to include, say, non-ideal MHD effects. So many of the calculations are done with very simplified physical set. So isothermal situations, a gas that's compressible, but purely hydrodynamic. So no consideration of MHD. And in the simulations, typically, but not always, the solid fluid, if you like, is not represented as a fluid, but rather explicitly as a collection of particles which move under the aerodynamic forces from the gas. Okay? That's not the only way you can do it, but that's the way it was done in these calculations I'm going to show you. There were no explicit collisions between the particles, and the runs I'm going to show were done with the Athena code, and self-gravity was done using quite a simple particle mesh scheme. So something to bear in mind is that the simulations that are mostly done of the streaming instability don't represent the exact same physical system which was looked at in the analytic work. So the analytic work was unstratified, okay, so there was no settling of particles towards the midplane. It was an incompressible fluid, and the particles were also represented as a fluid. Okay, so that's the analytic analysis of the system. This numerical analysis actually, in some ways, relaxes some of those assumptions, in part due to numerical convenience. Okay, so can't see this too well because the sun has now come out. But this is an illustration of the sorts of evolution that you see in these kind of calculations. So here you have the radial direction, the distance from the star. Here you have the azimuthal direction, so this is the orbital direction, and the colors here are showing the density of particles integrated over the vertical axis. And you have three different time slices here. And what you're looking at is, the first thing that happens is that you develop sort of roughly axisymmetric bands of clustered solids. Okay? So the particles sort of drift, but then that drift becomes inhomogeneous, and they start to pile up in these bands. Okay? So this is the point at which that cycling analogy, that sort of peloton analogy is really valid. You've created a very dense band of particles here that is slowing the radial drift of this band, and so more particles are coming in from the outside to join them. But as you can see, this is not a completely axisymmetric situation, has some additional structure, and then eventually some of that structure develops clumps, and the clumps collapse to form planetesimals. Okay. So these are calculations done at fairly high resolution. So these are about 512 cubed simulations for the gas, and with 100 million or thereabouts solid particles representing the particle fluid. Okay, so what do people find when they do these calculations? Well, the main thing is that you find that you produce planetesimals with something like a power law mass function. Okay? And what's typically found is that the mass function has a slope of something like minus 1.6. Okay? So if you plot the mass function, it has some kind of slope, and this is minus 1.6, or something like that number. Okay? So what does that say? Well, that says if you were to consider obviously the number of planetesimals, the number of planetesimals is dominated by the smallest objects. Okay? It's a decreasing mass function, as you would obviously expect. Okay? But if instead you consider the mass in planetesimals, so we integrate that, then what you're going to find is that the mass is concentrated at the upper end. Because once we multiply this by MP, we're going to get minus 0.6, and so when we integrate that, we're going to get a positive power. So the result from calculations is that you end up with a mass function where most of the objects are smaller objects, but most of the mass of the population is in the handful of the largest objects. Okay? And that's interesting and quite distinctive because it's obviously different from what you get, say, for the initial mass function of stars, which is steep enough that both most of the mass and most of the number is in the smallest objects. Okay? And it seems to be at least a moderately a moderately robust result. And if you then ask, well, what would the mass of the most massive objects be? So here's a numerical assessment of that mass function. For fairly reasonable parameters, the most massive objects are really quite large. Okay, so they might be maybe a tenth of the mass of Ceres, which is the largest asteroid in the asteroid belt. Okay, so instead of being kilometer-sized objects, you might be dealing with objects that are hundreds of kilometers in size. So in this picture, the sort of early collapse to planetesimals directly gives you large objects that are significantly larger than were typically assumed for the formation of planetesimals. Okay, and so that was one set of simulations done by Jake Simon. Here's some other simulations done by Schaefer and collaborators, which looked at larger spatial domains for the numerical simulations. Okay, so if we actually go back to the previous calculations, here you can see that in the simulation domain, there are actually only two of these bands of solids. Okay, so you might immediately ask, is the structure that was being produced in these simulations partly determined by the size of the numerical domain in which the calculations were carried out? Okay. So Schaefer et al. Looked at this in larger domains. So you had a number of bands and obtained a rather similar mass function. Okay, so it does appear that the mass function that would be produced from the streaming instability followed by gravitational collapse ought to have this top-heavy form. So if that's correct, it's quite interesting, and we'll come to that a little bit later. It has some implications for core accretion models for giant planet formation. Okay, so when we're forming the cores of giant planets, the traditional model is that those cores form from the collision of planetesimals. And that's possible if the planetesimals have relatively small sizes, because then those small-sized planetesimals are aerodynamically damped, and they have a low velocity dispersion, and they have a strong gravitational focusing factor when they collide with the core. We'll say what that means in a little bit. If you have these much larger objects, which are hundreds of kilometers in size, it's actually harder to get them to accrete onto planetary cores. So in some sense, moving to larger planetesimals, even though it accelerates the early stages of later planet formation, can make it a little bit more difficult later to build really large objects. Okay, and then this is just something we've been looking at more recently, how the streaming instability depends on the aerodynamic properties of the particles. So these are calculations done with different sized particles. So here we have dimensionless stopping time of about 10 to the minus 3. Here it's 0.1. Here it's of order unity. Okay. So as you go from very small particles to larger ones, you get successively less axisymmetric structure. So for very small particles, you see these very prominent bands of solids developing from the streaming instability. But then as you go to larger particles, that band-like structure largely disappears. However, when you look at the mass function actually turns out to not depend, as far as we can tell, on the size of the particles. So you still pick up this top-heavy nature of the mass function.
So are these are all in 3D simulations? Has anyone checked in just 2D for academic exercise to see you get like much stronger scaling?
Yeah, so the question was about differences between 2D and 3D simulations. So these are 3D calculations. There's been a lot of work done in 2D. You obviously can't study the collapse process in 2D. But actually I'm going to show in a minute to sort of map out the parameter space of where the clumping would be strong. Most of the simulations are 2D. And probably there's a little bit of difference between 2D and 3D, but we actually haven't really tested that in detail. Okay, so what would the picture be here? The sort of going back to the big picture. If this is how you go from small particles to large ones, to planetesimals, it's likely to produce these large planetesimals, perhaps with sizes in excess of 100 kilometers. And that requires a sort of two-stage process, because the streaming instability works best when the particles are already relatively large, in the sense of having a stopping time that is sort of getting to 0.1 or thereabouts. That would be the ideal situation. So the sort of general picture would be that there's collisional growth that gets you from micron sizes, dust sizes, up to small macroscopic sizes. There's then settling, which then gets you to a combination of stopping time and local particle to gas density, where the streaming instability is effective. That then gives you the extra clumping you need to exceed the Roche density. You get gravitational collapse, and then you've built your planetesimals. And so this needs enough mass in the right size regime, so you would expect it to vary with disk metallicity, with radius. If there are these zonal flows that are concentrating particles, those would obviously be good locations potentially for initiating this kind of instability and collapse process. Okay, so let me now say a little bit about later stages of planet formation, some other later stages of planet formation. And this is actually, in some sense, a follow-up of a famous work that was done by Safronov. So 1969, he published this famous book on the formation of the protoplanetary cloud and the formation of the Earth and the planets. And if you're sort of interested in a bit of historical detail, this is available for free online. So you can just go and download it. And it's really worth taking a look at because obviously observations at that time were extremely primitive. But there's really a great lot of physics that Safronov had right, based just on general considerations. And there's a particularly a wonderful spot where he came extremely close to understanding that MHD processes could be very important for angular momentum transport in protoplanetary disks. So this was 1969. He was aware of at least Chandrasekhar's work on the stability of rotating fluids. I'm not sure if he was aware also of Velikov's work, which was at the same time. And he actually mentions Chandrasekhar's result that when you add a weak magnetic field to a rotating fluid, it completely changes the stability properties. Okay? And he then says that that could be very important for the protoplanetary disk because even having a weak magnetic field goes from Rayleigh stability, needing the specific angular momentum to increase with radius, to a condition where the stability is just determined by the angular velocity. So effectively, he understood the importance of magnetic fields for the stability of accretion disks. But then, unfortunately, the next line in the book is basically a misunderstanding of something else Chandrasekhar did, which was to study the instability with a non-zero magnetic resistivity. And Safronov took the view that even having a non-zero, a very small magnetic resistivity, completely wiped out the MRI. Okay, and so he then actually abandons that line of reasoning and doesn't discuss it further. But it's a very interesting discussion, and there's many other interesting discussions there. One other thing I'd say is that I mentioned this in the public talk at the planetarium, and in doing so, I tried to find a picture of Safronov, and this was actually the only one I could find on the web. And there must be other pictures. He won tons of famous prizes and stuff. So if anyone ever manages to find a good picture, this is some blurry, low-resolution JPEG, please let me know. Okay, so how do things happen later? Well, in the classical picture, we assume first of all that we formed these planetesimals, and then the later stages involve the growth of those planetesimals through gravitationally focused collisions. Okay. And so there are different growth phases. It's quite a complicated story. There's runaway growth, oligarchic growth, giant impacts, and so forth. But if these collisional phases can occur quickly enough, the final outcome is at least substantially determined by stability. Okay? And by that I just mean dynamical stability of the orbits of a planetary system. So the way to think about this is in the simple situation where you have two planets, which are, let's say, initially on circular orbits with some separation. Okay? Now, for each planet, there's a characteristic scale defined as the Hill radius, which represents a balance between the planet's gravity and the tidal shear around the star. Okay? So the Hill radius goes as the planet mass to the 1/3 power, and the planet mass is ratioed to the stellar mass here. Okay? Now, if you have two planets, the system is sort of quite distinctive. The system is absolutely stable if the separation is large enough, basically where large enough basically means a multiple of the Hill radius. Okay? So if the planets are well enough separated, they will just orbit stably for all time. If they're closer than that, they are typically unstable, and they will typically develop crossing orbits and have a collision, or one of the planets will be ejected. Okay? Now, if you have a more complicated planetary system with many planets, then typically there isn't a hard stability boundary that says beyond that point the system is exactly stable. Rather, if the planets are really close together, they will be unstable on a short time scale. If you make them further apart, the time scale will become longer. But nonetheless, the instability time is basically something like the planetary separation, or it's a function of the planetary separation, roughly speaking, in units of the Hill radius. Okay? In a little bit more detail, it tends to depend on the planet mass to the 1/4 power rather than the 1/3 power. But basically, it's something like how far apart are the planets in terms of their mutual Hill radii. Okay? And so then what happens is that if you start with a system that has a very large number of protoplanets that are closely spaced together, that's very unstable. The orbits start to cross, the protoplanets collide, and then the separation of the survivors becomes larger in units of this characteristic separation. So the collisions make the system more stable, and they continue until the stability time becomes longer than giga-years or thereabouts. Right? And at that point, even if the system is not formally stable, it's stable for practical purposes because no more collisions will occur over the lifetime of the star. So this is how this works in the inner part of a planetary system. So here you have distance from the star. Here you have a bunch of protoplanets that have been laid down with initially small eccentricities. And here you're just looking at the build-up of that mass between 1 million years and 100 million years. Okay? So you start with a lot of objects, low eccentricity. Some of the objects start to grow. Their eccentricities are damped by the sea of smaller objects. And then you build up just a handful of very large objects on a time scale here of about 100 million years. Okay. So this is the sort of standard picture for how you make the terrestrial planets in the solar system. You start with a few Earth masses of objects laid down between half an AU and a few AU, and you just let them grow under mutual collisions. Okay. And that works to make, you can see you've made here 4 large planets on a time scale of about 100 million years. Okay. Now there are many, or some aspects, let's say, of the solar system which this kind of simple picture doesn't reproduce very well. One is that if you sort of look at the masses of the terrestrial planets, you have Venus and Earth, which are sort of roughly comparable. Mercury is very small, probably has some unusual formation history. But Mars is significant, but it's much less massive than the Earth and Venus. And in most models of the disk, you'd have more mass out where Mars is than where the Earth is. So you might, if anything, expect a larger Mars than the other terrestrial planets. And that's observationally not what is found. As you can see in this simulation, the 4th red band that's forming here is actually even larger than the other ones. And so here this is producing a large Mars. Okay. So the small mass of Mars is a bit of a problem. The small observed mass of Mars is a challenge to some of these models. But generally speaking, this can sort of explain the masses, the eccentricities, the inclinations of the terrestrial planets pretty well. Now, what about the giant planets? Well, for the giant planets, the basic picture is that you form a core of a number of Earth masses, maybe 5 to 20 Earth masses, from the accretion of these planetesimals. In the standard picture, it's these kilometer-sized planetesimals that collide to form the core, and then once the core has reached these many Earth masses, it's continuing to grow as more planetesimals are hitting it. Then the core is then surrounded by an atmosphere or an envelope of gas which has been accreted from the disk. And initially, the mass of that envelope is not too large, and the accretion of more gas is limited by the rate at which heat can flow out through the envelope, allowing the gas to cool and contract to higher densities. Okay? So what matters is the opacity in this envelope, which is preventing or slowing the escape of energy from the envelope back into the protoplanetary disk. Okay? But as time goes on, the envelope cools, it gets denser, and then once the envelope has a mass that's roughly comparable to the mass of the core, the envelope itself becomes unstable and collapses, or at least contracts rapidly, to form a dense envelope, and then more gas piles on, and you form the envelopes of the giant planets. So these are some calculations of that. This is time, this is mass, this is the growth of the core, and then this is the growth of the total planet mass. First of all, you grow the core, then you slowly pick up an envelope, and then eventually you get a runaway phase of gas accretion. So the key point about this is that this requires that you get a lot of gravitational focusing of the planetesimals onto the core. Okay, so by gravitational focusing, we simply mean that if we have the core here, what we need is for planetesimals coming in to be deflected by the gravity of the core itself, so that the effective cross-section for collisions onto the core is much larger than the physical size of the core itself. Okay? So that gravitational focusing depends on a factor like this. Depends on the escape speed from the growing core, v escape, and sigma, which is the velocity dispersion of the objects that are trying to accrete onto it. So it requires a dynamically cold population of planetesimals so that this factor is very large. So normally for giant planet formation, we want this factor to be something like 10 to the 4. Okay, so it really needs to be a very strong gravitational focusing of planetesimals. And as I was saying, that's easier if the planetesimals are small, because if they're small, they have some aerodynamic damping, and so you can keep their velocity dispersion low, despite the fact that you have this giant planet core, which is trying to kick up the velocity dispersion and heat up the population. Okay, so that's the sort of classical picture. The extra element that has been considered in more recent years is late time dynamical evolution of the system. So let me show here. This is the so-called Nice model for the solar system. And so to explain some puzzles in the outer solar system, what's generally assumed now is that the giant planets, so this would be Jupiter out to Neptune, initially formed in a more compact configuration. Okay? And they were surrounded initially by a rather massive belt of planetesimals, which would be the primordial Kuiper belt. Okay? So this would be maybe 50 Earth masses in small icy bodies, extending up to the mass of Pluto. And the picture is that there would be an instability in the orbits of the giant planets. There it went. Which would cause them to interact with the planetesimal disk, to scatter the planetesimals, and to actually move outwards radially. Okay, so what's happening here is that as the planets move outwards, they scatter planetesimals inwards, and then the planetesimals reach Jupiter, and then they get ejected from the solar system. Okay, so in this kind of picture, let's play that one more time. In this kind of picture, a lot of what we see in the outer solar system would be the outcome of this kind of instability. Okay? So this is actually what I'm showing here is a movie of the original Nice model. So this is Siganis et al. From 2005. There are more recent versions of this model which changed some important details, but the basic picture remains the same. You started with the giant planets closer together. You had a lot of material left over. And a lot of what we see in the outer solar system is based on the interaction between the planets and that surviving planetesimal disk. Okay, so that's the solar system. Here's a simulation of the same sort of thing for extrasolar planetary conditions. So here you've got 3 giant planets. You've got a massive Kuiper belt. And here you're looking also at terrestrial planet formation on scales of about 1 AU. The colors here are showing the water fraction of the objects that are growing. So here again, you're going to get an instability among these giant planets. Here it goes. And the instability basically clears out a lot of the material, both from the outer disk and from the inner terrestrial planet region. Okay. So here you just get one terrestrial planet surviving on a very eccentric orbit. Okay. So for extrasolar planets, this is of interest because we observe a lot of giant extrasolar planets to have eccentric orbits. Okay, so the picture might be that planetary systems typically form with unstable orbits of the giant planets. In the solar system, that instability happened, but the interaction with the planetesimal disk was strong enough to damp the orbits back down to being almost circular, which is what we see in the solar system. Perhaps in extrasolar planetary systems, where the planets are sometimes closer to the star, the instability happened, but there wasn't the same damping to bring the planet orbits back down to circular. So instead you end up with giant planets which have quite significant non-zero eccentricities. Okay, so what are the problems with these kind of stories? Let me actually skip over that because we'll go on to something else. Okay, so a question we have is, how does this kind of planet formation story fit in with what we see from Kepler? Okay, so so Kepler has observed many planets mostly in orbits fairly close to the star. Okay, so here's a plot of some Kepler results. So Kepler saw maybe 4,000 extrasolar planets, right? So a very large number. But for most of those, we only know the radius. Okay? So that obviously doesn't tell us all that much about the nature of the objects. But there's a smaller subset where we've been able to measure both the radius and the mass. Okay? So when you do that, you can obviously produce a density and get an idea of what the internal structure might be. So that's what's plotted here. Here are the mass of planets in Earth masses and their radii also in Earth masses. So here's Earth, here's Venus, up here is Uranus and Neptune. Okay? And these curves here show the radius-mass relation, so the density relation, for planets with structures made up of different materials. Okay? So these are interior structure models for planets. So this red curve is a planet made of 100% iron. Okay? So that would be basically the densest object we could imagine forming. And so that would have the smallest radius for any mass. That's 100% iron. This is a curve with a large amount of iron surrounded by less dense rocky material, silicate type material such as we have with the Earth. Here we have again lower iron content. Here we have a model with 100% water, so a world that's completely made up of water. And here we have a planet that has no heavy materials at all. It's just made up of hydrogen and helium. That's the least dense. Okay? So what you see here is that Kepler sees a number of planets which have densities that basically fall on the same composition tracks as are inferred for the Earth and Venus. Okay? So you might reasonably say that those could well have similar compositions to our own terrestrial planets. It also sees some low-density planets that fall in the region of parameter space where we see Uranus and Neptune. Okay? But there's a large bunch in the middle which have both masses and densities which don't really map onto any solar system objects. So these are called super-Earths or mini-Neptunes, and indeed they might be scaled up versions of the Earth, so rocky planets but with larger masses than the Earth. They might be scaled down versions of Neptune, so cores of basically icy material surrounded by an Earth mass or two of hydrogen helium envelopes, or in the intermediate region they might have structures that are distinctly different from any solar system planets. So we don't really know what's going on with those objects. Okay, so what new ideas are around to try to explain some of these problems? Okay, so one idea is pebble accretion. Okay, and the idea of pebble accretion is that when you have a planetary core, so it might be the core of a giant planet, or it might be a lower mass object when you're thinking about terrestrial planet formation. In the classical picture, that object grows by accreting other planetesimals. Okay, so it grows by accreting at least kilometer-sized objects. And in that case, the dynamics is almost entirely just that of gravity. Okay? However, we know when we look at protoplanetary disks that there's a lot of small solid material which is present in those disks even at late times. Okay? So the idea of pebble accretion is that maybe some of these planets are actually growing not from accreting planetesimals, but rather from accreting small particles that might be in the size regime of centimeters or thereabouts. So the basic picture would be that you have your gravitating object, your protoplanet, and then it has some scale around it which would be set by the speed at which these particles are encountering it. And that would be described as the Bondi radius. So the particles come in, they experience the atmosphere around the planet, and then if they're close enough, they spiral in and are accreted. Okay, so effectively, the planet, which is very small, has a very large capture cross-section for the aerodynamically assisted accretion of these pebble-sized objects. So under some regimes, the rate at which you could accrete these small things could be vastly greater than the rate at which you accrete planetesimals. So whatever radius you are in the protoplanetary disk, you could accelerate the formation of larger objects very substantially if you have a large drift of pebbles to come in and be encountered by these planets. Okay. So, this could sort of in some ways fit in with this story of planetesimal formation. I was discussing a model for planetesimal formation that involves growing up to millimeter or centimeter sizes, and then those sizes collapsing to form planetesimals. If that happens, the planetesimals then grow into protoplanets, and the surviving pebbles, perhaps, are very important for the accretion onto those objects and growing them to larger sizes. Okay? So this is a popular model that people are exploring now. There's still a lot of details that remain to be worked out, but at the very least, it represents an alternative channel for going from, let's say, protoplanet sizes up to full planet sizes, which in some cases might be faster than the classical way of doing things. There's then another consideration that people have had, which is to do with envelope accretion. So in the classical picture of planet formation, what you have is you have a growing planet, might be a giant planet, and you have some scale which defines how far out the gravity of the planet dominates over tidal shear in the disk. Okay? So that scale would be this hill radius, which just goes as the 1/3 power of the planet mass times the semi-major axis. Okay. And in the classical picture, the atmosphere or envelope that extends out to the hill radius is all in hydrostatic equilibrium. Okay. So if you're asking how quickly that envelope can cool and more gas can accrete onto the planet, you basically have a stellar structure problem, except with a solid core in the middle, which changes things a little bit. And you have to just ask, how quickly can energy flow out through either convection or radiative diffusion? Okay. And in some cases, particularly when you go to large distances away from the star, that timescale becomes very long. And if we go close to the star, sort of in the region where Kepler is observing planets, it's not completely clear how you produce planets with the sort of envelope sizes that are seen by Kepler. Okay. Now, this picture has recently been challenged by numerical simulations. Here's one by Lambrechts and Lager from last year, which look at the three-dimensional structure of gas flows around growing planet cores. Okay? So here you have the planet, and here you have just some streamlines of gas coming in from the protoplanetary disk to the region where the planet is. And the key result of these simulations, and there's a bunch of other ones here, D'Angelo and Bodenheimer, Chris Ormel and collaborators and so forth, is that gas that is initially in the disk, and therefore is unbound to the planet, can actually circulate well inside the Hill sphere and then flow out again back into a trajectory that joins it to the disk. Okay? So this means that the sort of the standard picture of how these planets with gas envelopes cool is not quite correct. Okay? The atmosphere around them is not hydrostatic all the way out to the Hill sphere. Depending on the equation of state, the outer part of the envelope may actually be being continuously sort of circulated between the disk and the planet. So in that case, the outer part of the planet can cool neither radiatively nor convectively. It can cool simply by being swapped back out into the disk, where there's more surface area, and it can cool radiatively. Okay? So this is an aspect of physics that is of interest. It's very relevant to this distinction between Kepler-type planets and the things we see in the solar system. And this is, again, something which people are looking at quite actively at the current time. OK, so I think I'd better stop there and can have some questions before lunch. questions?
Just have a curiosity, and I was thinking that meteors and comets should trace somehow the history of the protoplanetary disks. And so, if so, if you see some, for example, chemical reaction or processes of like rock fusion in meteors or comets, they should have formed at the gravitational conditions and physical conditions of the protoplanetary disks. So it should be required like some kind of degree of like gravity and yes, gravitational bounding of the elements on the protoplanetary disks. And I don't know if these things are being compared, for example, with the observations, and in case of this like physical requirements for the morphology are feasible with the physical scenario.
Yeah, so it's an interesting question. So, so the question was, say, what can we learn from looking at asteroids and comets, from the structural properties of asteroids and comets that might constrain these kind of scenarios, right? And I think there's a tremendous amount in principle that can be done, right? I mean, for asteroids at least, the general expectation, which I think is consistent with what is seen from in situ observations by spacecraft, is that most small asteroids are made up of so-called rubble piles. So they're basically small pieces of rock which are just like sitting on each other gravitationally, right? That's sort of basically the picture we have for those. The difficulty with the asteroids is that we know that the asteroids we've observed the best are the near-Earth asteroids, and we basically know that those are collisional fragments of larger asteroids that were in the asteroid belt. So they've been processed very heavily since the planetesimal time. When it comes to the comets, it's less clear. I think there's obviously a question. What size would you predict for primordial planetesimals in the Kuiper belt, and is that much larger than the main reservoir of comets? Because if so, that poses perhaps a challenge. There are other things you can imagine looking at, such as how frequently you form binary planetesimals, because we know that there are binaries in the Kuiper belt, and it's not actually completely easy to understand how all of those binaries formed. So there's a range of observational things that people can look at. At the moment, that it's quite hard to make a direct comparison. People have done models for the evolution of the asteroid belt in particular, which would be consistent with having large primordial planetesimals, but I don't think the modeling necessarily says that the primordial planetesimals have to be large. So it would be consistent, but it's not particularly strong evidence, is my feeling.
If I understood correctly, in the NIS model, all planets of solar system have formed inside 20 astronomical units. It looks quite compact compared to other planetary systems we observe. What is more common process, compact systems or more large systems?
Yeah, so the question was relating to the scale of planet formation in the solar system compared to extrasolar planetary systems. So I think one of the motivations for the NIS model originally was the fact that the timescale for forming Uranus and Neptune, the theoretical timescale for forming Uranus and Neptune becomes large once you get much beyond 1015 AU, right? So in particular at Neptune's distance, it's really quite hard to imagine forming the core of Neptune. Okay? And the reason for that is actually something I didn't really mention, but if you imagine just a gravitating object embedded in a sea of planetesimals, then as you go further out, there's a comparison between the escape speed from the surface and the orbital speed of the planetesimals. And as you go further out in the planetary system, it's more likely that gravitational encounters will lead to scattering rather than accretion. So you just don't accrete those objects. Okay. So one of the motivations for the NIS model was that by making everything smaller, you alleviate those time scale constraints. So I think that's still, that's still quite plausible, or that's still a correct argument. Obviously, with pebble accretion, you have some extra flexibility, right? So you could imagine growing things via that mechanism, and it's not really subject to the same constraints as planetesimal accretion. When it comes to extrasolar planets, we do observe some systems where there are planets at large radii, but it's really only a handful. And direct imaging surveys have not really found very large numbers of planets out at large distances. So the extrasolar planet situation would also be consistent with it being hard to form things much beyond 20 AU. And the one complexity there is, okay, we have these ALMA images of protoplanetary disks where we see a lot of structure in the disk at those very large scales. So that's where there's some tension, actually, right? If those structures are due to planets, that's saying actually that we must be able to form them quite easily at those scales. But then the direct imaging observations are saying that at least at the most massive end, we don't have many planets. So I think you could pick different versions of that, right? You can either say the structures we see in disks are not due to planets, and really planet formation mostly occurs quite close to the star, or you can say, we are seeing planets in those disks, in which case we have to, appeal to these faster formation channels.
When you show this evolution of planetary systems in the R eccentricity, radius eccentricity plane, there are some error bars in vertical direction. What are these?
Yeah, so this is related to the movie I showed of the simulations. I didn't explain what the error bars were. They weren't actually error bars. They were actually visualizations of what the inclination of the orbits is. So that was showing what the tilt was in the third dimension.
The larger they are,
The more, yeah. So in general, in these kind of scattering scenarios, you develop both eccentricity and you develop inclination. So they tend to trade off.
What kind of values inclination has?
I forget now exactly what values, but they would be like of tens of degrees, probably that kind of value.
So in your simulation, in this 2D simulation, some of the planets gain quite high eccentricity, and probably they could cross trajectories of each other. What would happen if they collide in the simulation?
Yeah. So the question is, what happens if planets collide? So in the dynamical simulations we've done, they accrete perfectly. In reality, when two planets collide from unbound orbits or from orbits, most of the mass probably does end up getting accreted. So the velocity is not high enough that it's going to just blast everything to pieces. But you can get some material, ejected back into orbit, right? So these are so-called hit-and-run collisions. So if you particularly have a glancing blow between two planets, most of the stuff will be accreted, but you'll get some debris thrown out, and most of that will normally be reaccreted within a fairly short time. But exactly how much is reaccreted and whether you could sustain some population of smaller bodies from those fragments, that's also something that is quite hard to calculate, actually.
So kind of on that note, is it are simulations like the ones you showed consistent with the formation of the moon as like a collision fragment? Do you see scenarios where that's happening?
Yeah, so the question is, are these simulations consistent with the formation of the moon? That's not something we looked at. It's something other people have looked at. Broadly speaking, yes, right? There are enough late impacts of about the right size that, with the large error bars, we have one moon, and we have Earth and Venus. So we have a 50% large moon fraction in the solar system, right, with some enormous error bar. It would be basically consistent with that, right? I mean, trickier is to estimate the range of collisions that could really plausibly give rise to the moon. So, the standard picture is that the moon was formed by the collision of the last collision of a Mars-sized embryo with the Earth, okay, with some particular value of angular momentum. But there's been more recent work discussing, what range of impactors could potentially produce you a moon. Could you have a lower velocity impact with a larger body, and so on and so forth? And so that question is still a little bit open, and it's mostly driven by different models for trying to explain the chemical composition of the moon.